Another concept that's useful from our study of natural ecology is this term called population ecology. So here we're not studying just one organism, we're looking at multiple organisms of a species or even organisms from other related species. So we are looking at entire populations, we are looking at what we call their spatial distribution. How are they spread over an area? We are looking at what's called their temporal dynamics. That means temporal means over a period of time. How does this population evolve? Do they increase? Do they decrease? Do they scatter? We are looking at their demographics. What is this made up of? What is savanna made up of? Who are the inhabitants? And we're also looking at their evolution. Over a period of time, what happens? Sometimes there can be displacements. So that's what population ecology is about. It's not about individual members, it's looking at the entire population to study. You remember earlier we said ecology was a study of organisms and their relationship with the environment. Here we're not just looking at an organism, we're looking at entire populations or groups of related species and trying to learn from that. Well, when you apply these concepts to industrial or technological organisms, the analog would be that we study factories or groups of related factories, but that doesn't contribute much to our goal of sustainability. So what we do here instead is we don't focus on the factory, we focus on what the factory does, which is produce products, because it's products that's the key thing around which a factory is designed and built. Now, even when we talk about products, we don't care so much for the absolute number of products made. We care to know how much, what is the potential resource utilization, and then the potential environmental impact because of this product design, development, and evolution. You see, I may make more of product X and less of product Y, but if product Y on average consumes more resources, that will be more environmentally impactful. So it's not just the numbers, but the relative resource utilization and the consequent environmental impact. And so the resource consumed by a product or a product family, right? What do we mean by product family? It could be similar metal cast products in an automobile. You have the engine cylinder, cylinder head, it could be a connecting rod, crankshaft, so that's a product family, right? So the resource attributable to a family consists, can be determined by the size of the family, how many per year, and the resource consumed by just one member of the family. So you multiply one against the other, you get the total resource consumed. So I have a formula here. Alpha I is the average resource consumed in absolute by a product family, where Q is the size of the family, how many, 100, 1,000 per year, and UI is the average resource consumed by one member of the family. I will illustrate how this is applied in just a bit. Sometimes we find it more useful to talk about relative resource consumption rather than absolute. So you get the relative resource consumption, rho I, when you divide the absolute resource consumption by a term called Ri. So here the term I refers to which resource we are talking about, right? If you take an automobile, it uses multiple resources. It uses aluminum, it uses steel, it may use wood for upholstery, plastic, glass. So I1 could mean aluminum, I2 can mean steel. So this is the formula that helps you calculate resource consumption, both relative and absolute, for the ith resource. Let's say I equals 1 is aluminum, right? So Ri is the average, is the annual consumption of aluminum for all users of aluminum. So let's see, we can take a look at this by plugging some numbers. Right now it seems very abstract. So there's a table in your handout. So it is this table here, And what we're looking at is aluminum resource consumption by automobiles, right? So I stands for aluminum, and that in this 1980, as you can see, there were 28.6 million vehicles sold. So that's your Q, that's your volume. Each of these vehicles consumed on average about 60 kilograms of aluminum. So when I multiply Q times UI, volume times amount per vehicle, that's about, you know, 1,716 kilograms per year. Now we know a metric ton is 1,000 kilograms. So if I divide this by 1,000, I get 1.7. That is so many tons per year. So that's how we get this 1.7 you see in the form in the table here. Now to find the relative consumption of aluminum, relative to what? Relative to other uses of aluminum. Because aluminum is not only used in cars, it's used in a lot of things in your house. For example, if you have a sliding glass door, the frame and the rails are made of aluminum. Some of your utensils may be made out of aluminum. Most of your beverage cans, whether it's beer or Coke or Pepsi, they are made of aluminum. So aluminum is used for many other things. Ri here 15.4 shows aluminum used for all purposes. This gives you aluminum used just for automobiles. This is for all. So when you divide, and it's 0.11, that means 11% of aluminum in 1980 were used in the automotive sector. The rest. Now, if this is equal to 1, what does it mean? It would mean that all of the aluminum consumed in 1980 was used by the automotive sector. So one of the goals in industrial ecology is to try to reduce the relative resource consumption. You can reduce this by decreasing Q, decreasing U, or increasing R, right? If you increase the denominator, it goes down. Now Q is the volume. That means if we reduce our appetite for automobiles, it's desirable. I don't know how much it's possible. The second thing is reducing the amount of aluminum used per vehicle. Well, that is desirable, and technology can enable us to do this. Year by year, we seem to do better. So technology can help us use less aluminum or any other material. It's called dematerialization. Ri is the amount of aluminum used for all purposes. If you increase R, the amount comes down, but think about it. It makes mathematical sense, it makes no common sense, right? Because why would you want to increase the amount of aluminum consumed in a year for all purposes? That seems to be depleting some of our precious resources. There's another formula that's not in your handout, which is this. We can also talk about the environmental impact, and we have the subscript J. So environmental impact of the jth kind given by epsilon J. So what do we mean by of the jth type? There are different kinds of environmental impact. There is global warming potential. There is the acidification, which means creating acid rain. And then there is eutrophication, a process where a lot of salts, nitrates and phosphates get dumped into lakes that causes accelerated growth of plants. Well, these plants then consume a lot of oxygen in the water and choke the fishes. So it's called eutrophication. So there are toxicity. So there are different kinds of environmental impact. So J1, J2, J3, J4 can stand for different types of environmental impact. So epsilon J, absolute impact due to a product family, is equal to P, the product family size, times Ij, that is the impact per unit of product, multiplied by the volume will give you the total. Sometimes you may want to know just the relative, not the absolute. So phi j is the absolute, P times Ij divided by phi j, which is the phi in the bottom, uppercase phi, is the total environmental impact due to the jth impact due to all kinds of industrial activity. So acidification can be caused by mining, it can be caused due to agriculture, it can be caused due to transportation. So the totality of acidification is given at the bottom. Now, if this ratio is equal to 1, that means all of the environmental impact of a particular kind is caused by this one particular kind of product. So these are ways in which we can quantify resource utilization and their consequent environmental impact.